Hi, everybody. Good morning. I hope you're well. So, before we start, I think we should talk about the assignment. I prepared the assignment, but I was waiting for one more discussion before I announce it. I was thinking something. Instead of giving you two assignments, I could actually give you one that will be broad. So, I'm considering this. What do you think? What would you prefer? Two short assignments or one major assignment? It's assignment concerning the course. For this course, it's not a programming task. It's just related to the content of the course. Here is my consideration because um, these assignments will assist you in doing revision. So I'm thinking I could give them to you at once. You solve them, and as you solve them, it appears as if you are revising for the course, revising for the exam. Or I can split them into two halves. A first half will consist of the things that we have done absolutely. The second half will consist of, I think, some things we've done and the rest that we have not done. So here's my thought. I can give you everything as just a single assignment, or probably I can push the two to you as two separate assignments. Maybe I can send them at the same time. Um, I just wanted to decide on this. But if you decide not to decide on it, I can send them as two assignments, different PDFs today, and set different deadlines for them. Okay, probably that would be better in case. Okay, so I think that would be the solution. Two tasks all sent today, different deadlines. All right. Okay, so we'll do that. Let's continue with our integratability. So we've talked about a number of attributes situation, and we have talked about maintaining response for each attribute. We want to make sure that the response we provide to a stimulus concerning an attribute's downtime or an attribute's the challenge with an attribute assists us to mitigate the consequence of this challenge so that we can have some better response. And now we are talking about integratability. So we all have a partial understanding at least that software systems are built in parts. And so we have to integrate them. At the point of integration, we could have a problem. And that's why we are discussing integration. We are discussing how we can avoid having this problem. So here is our previous example. We were talking about a system that just got a new component in the data marketplace. Okay, so we have a new data filtering component just became available in the component marketplace. The new component is integrated into the system and deployed in 1 month. So we do a deployment, and this takes a time of 1 month with no more than one person month effort. So actually, we are expecting one person to work on it in 1 month. So that is one person month. So this we can convert to concrete scenario diagram. So the source is the marketplace. So a new component just arrived in the marketplace and we want to put it in our system. We want it integrated into our system. So the stimulus is the component arrived. And we said we are integrating it into our system. So, when are we going to integrate it? What is actually happening at the time when we are going to integrate it? We said it should be a deployment process. And so this would be the environment, the deployment environment. We got the new component during a deployment phase. And so after introducing this new component to our system, there is expected to be a response. And the response is that the new component is successfully integrated and deployed. So what would be the measure of that response? For the time it spends to be deployed, we used 1 month and 1 person per month effort. So it was deployed within 1 month by just a single person. Okay. Yes, we discussed this the other time. Goal of integratability tactics. The goal of integratability tactics are to reduce the cost and reduce the risk of adding components to each other or of integrating components or integrating change components and integrating set of components together to fulfill some changing requirements. Okay, so we begin to talk about the tactics here. Okay, so this is just the goal of integratability tactics for the last example that we had. A new component arrives in the marketplace. We set up some tactics to handle the response. And at the end of the day, we were able to achieve our expected aim. I mean, this is for the last task. But on a general note, we have integratability tactics. And these are tactics to ensure that we are able to integrate components successfully. So first is limit the dependencies. I believe this should make clear sense. You have different components that are to operate as a whole. It's important to reduce the dependencies of components on multiple other components. Make sure that dependencies are as reduced as possible, such that each component doesn't have to communicate with too many other components before it can function. And to do that, we have a number of tactics. One is encapsulate. Make sure that you encapsulate them. Separate individual functionality, separate them as part. Where components may not directly work with each other, find an intermediary. Restrict communication part. Ensure that we don't have too much unnecessary dependencies. Restrict communication part. Enforce that communication takes specified parts. Adhere to standards. Okay, don't write codes and expect execution based on your opinion. Stick to some programming standards, and then abstract common services where multiple components provide some similar services. Abstract the parts that are different and make sure that the parts that are similar are implemented by a single system. Next is adapt. Discover services that can provide some functionality, tailor the interfaces so that they can meet these demands, and configure how each system behaves, how each module behaves, how each component behaves based on its current situation, maybe based on its current interface communication. Decide how each component behaves. And also we have coordinate. Coordinate the components, we orchestrate, and then we manage the resource utilization. All right, so we start from here. Limit dependencies. To limit dependencies, just like I explained earlier, we need to make sure that we encapsulate. When the parts of the code system are just all over, there is no form of encapsulation, there is no form of specialized professional grouping. Actually, everything will depend on each other since there is no encapsulation, there is no packaging. So, in order to reduce dependencies, to make sure that whenever you want to add a new component, whenever you want to integrate components, it is easy to integrate since you understand a specifically defined interface. Then you must make sure that dependencies are reduced such that interfaces are the only means of communication. Encapsulate. Encapsulation introduces an explicit interface to an element and ensures that all access to that element passes through this interface. This is the idea about encapsulation. You encapsulate. Like in Java, generally in object-oriented programs, one thing we can do is that we can create classes. And from these classes, we can probably have subclasses, we can have inheritance, and a number of things. But the idea is that a class that does a specific job should be grouped with all the methods and the properties that are for this job. And this way, anything that needs to communicate with this class communicates using predefined methods. And this is why we say it is important to encapsulate. By encapsulation, we enforce that group of codes that do a specific job are grouped together and only communicate using their provided interfaces. Dependencies on the element's internals are eliminated. So what this means is that another class cannot change variable x in a different class. Another class cannot create objects for a different class without actually going through the predefined interfaces. So the predefined interfaces assist us in enforcing the behavior of that class. So dependencies on the element internals are eliminated because all dependencies now must go through the interface. Probably, I am not certain, but probably you have seen a code in which variables are defined inside of a class. The variables are made private. The class itself is made private, but we have a constructor inside of it that does a specific job, but that constructor is made public. So what are we trying to do? We are trying to enforce encapsulation and ensure that everything that happens inside of that class is done only based on the interface. Only based on the interface. Use an intermediary. So intermediaries are used for breaking dependencies between a set of components. Intermediaries can be used to resolve different types of dependencies. All right. So there are times that we may have a few dependencies, but we need to break them. One way to break them is by using an intermediary, a guy that can receive information from a dependent A, passing it to dependent B, but ensuring that the way they communicate is under a specific control. That control is set by this intermediary. So this intermediary is just like a middleman who places policies on two parties that are trying to communicate. So he says that, okay, party A, you speak only in English. Party B, you speak only in English also. When you speak English, there are some words you must not use in your communication just to ensure that there is peace. So this is what the intermediary does. It provides communication between components, and in that process, it breaks dependencies. Next is restrict communication path. This tactic restricts the set of elements with which a given element can communicate. Restricting communication path, it blocks the set of elements, it controls the set of elements with which a specific element can communicate. So we could have components for doing a number of activities. Let's say we have different components, one for getting the user information, another for getting login criteria. We have different elements as such. We can establish that some components should not be able to communicate with other components using law of least knowledge. So if you don't need to be able to communicate with a specific component, you shouldn't even do it at all. And that is restricting the communication part. Communication from a component should not go in a direction of another component that it does not require. That's the idea. Next, limit dependencies. So we adhere to standard. Okay, so we discussed two. Next, we adhere to standard. Standardization in system implementation is a primary enabler of integrability. Why? Because there are standards for defining interface and communication. There are standards. So adhering to these standards actually solves a number of problems before they even begin. So adhere to standards. Standardization in system implementation is an important enabler of integrability and interoperability across both platforms and vendors. Some standards focus on defining syntax and data semantics. Others include richer descriptions, such as those describing protocols that include behavioral and temporal semantics. So here is the idea. In order to ensure that dependencies are reduced or dependencies are actually broken, we need to stick to standards that define how systems should communicate. Example is you want communication between two component parts of different systems. How would that be done? You do it over a network. But the fact is, over the network, a protocol must be defined of how to communicate over Ethernet. So in this situation, probably let's say you use TCP, you must stick to the requirements of TCP. And this is the idea behind adhering to standard. Adhering to standard assists us in sticking to some predefined policies. Abstract common services. When two elements provide services that are similar, find the parts that are similar in it. By the way, it should not absolutely be similar. I mean, if they are providing completely similar um, duties, then why do you make them two different things? Just use only one. So we expect that they are not going to be completely similar. They are going to be very similar, but probably with just a few differences. In this situation, it is important to hide them behind a common abstraction. Hide them behind a common abstraction. Only the need to know are presented. This abstraction might be realized as a common interface that is implemented by both. So, as a common interface that is implemented by both, or it might involve an intermediary that assists in providing some sort of translation between the two parts and understanding that they have differences. Understanding that they have differences. So we move to the second part. Remember, we are talking about two parts. One is limit dependency, and the second is adapting to the situation. So we have component parts that need to find a way to adapt to the system they're integrating into, or to adapt to the demands of the other component parts they need to communicate with. And the first thing is discovery. For it to for them to actually communicate, they need to identify each other and have some discovery of services provided. So a discovery service is the mechanism by which application and services locate each other. So when they locate each other, a log is made. This registration can happen statically or it can happen dynamically when a service is instantiated. That's all right. So the idea behind this is just that we need to have a discovery mechanism, a mechanism that allows components to be able to advertise their services and then allows components to be able to identify the services advertised by other components. Tailor interfaces. So tailoring an interface is a tactics that adds capabilities to a an interface. Okay, this is just the idea. We have an interface that can perform a specific task, but the point is that it doesn't perform that task to just one to just one other component. It performs the task to different components, but there's a specific component that needs to have little knowledge of all of its functionalities. In this situation, what we have is to tailor the interface. We have to tailor this interface such that it advertises the required set of functionalities to each specific type of component that tries to communicate through the interface. So we have some components that try to communicate through the interface and they require 7 services. Advertise 7 services to them. The other component that requires only 2 services, find a way to make sure that this interface does not advertise all its available seven services. Make it advertise only 2 of the services the component requires. This is actually the meaning of tailor interface. Okay, tailoring an interface is a tactics that adds a capability to an interface or removes capabilities from an interface without changing the code. So the idea is just this: whenever an interface, a component tries to make contact with a different component, there is an exchange of identity, and so the component providing the service identifies the requirement of the component trying to get the service, and because of that, it adapts its interface to the requirements of the interface. So capabilities such as translation, buffering, and data smoothing can be added to an interface without changing it. So example of what this is that if you have component parts that make use of raw data, and then you have component parts that make use of, let's say, a log normalized data where the spikes have been smoothed out. What do? We have to tailor the interface such that the parts that require fine details receive the log normalized information, while the parts that do not require details receive the raw information. Behavior must also be configured in order to adapt to the different components. The behavior of a system of a component can be configured through the build phase, that is recompiling with a different flag. Different flag here means that recompile with probably a variable, a specific value that changes critical components in the code. This is just the meaning. So let's assume we set a variable flag to control a case switch. We can alter the behavior of the entire code by just changing this switch variable. So we can configure it during the build phase or during system initialization or during runtime. So during system initialization, we could have something like a JSON file where the system reads. So we can have a JSON file. It could be a DAT file, any kind of file that can provide information, or a binary file, a bin file that can provide information during initialization. So this assists the system to be able to change its behavior, based on some kind of expected component communication. It could be at the build phase. It could be during the system runtime. By the way, build phase means during the code compilation. So during the time you are compiling the code, this is the only time you can change flags. So at the build phase, you can alter some variables that decides on the process of code execution. But after this phase, you don't have access to the build phase anymore, but you can have access to the system initialization phase. This is the phase during which the component tries to get the information of the system in order to build itself for that platform. By the way, probably you have an idea of this, that when you try to install some software on a system, one of the first things it does is that it checks the information file of the system. checks the kind of CPU it has, checks the kind of display graphics it has, check the size of memory it has, and checks a number of things and decides on the variant of the software to be installed. Um, I, this is a this is a common thing I believe in Android environment, where we can have a software developed for multiple APIs deployed into the Play Store, and depending on the API level of the mobile phone that is trying to fetch this file, the system dynamically decides the appropriate one. So something similar to that is what we are discussing here. During integration, this system is investigated. So the component checks the configuration of the system to decide how it would operate, to decide what kind of settings would be used in operation. And this is an example of a configuration file. So we could have a boot up configuration file that right from startup tells the components how to behave, or during runtime. So at runtime, this software is already executing. Not a lot can be changed, but actually some things can be changed. At runtime, even though the software is already loaded into memory, we need to understand that communication is about to be done. We need to understand that processing of data is just yet to be done. And because of this, we can still change how the system behaves. You can change how the component behaves during this time. We can check how the component behaves. So we can specify a protocol version that is required from other components as part of requests. So this way we are adapting to the demands and the behavior of other components to be integrated. And finally, we can coordinate. Uh, the first here is to orchestrate. So we use a control mechanism to coordinate and manage the invocation of services so that they can remain unaware of each other. So this is just the meaning. It's just like a conductor. Probably you have seen the opera or some kind of music performance. You see the conductor stands in front of the choir, he gives them direction on how to behave. But the idea is this: the choristers do not look at each other, the choristers look at the conductor. And so this is the same idea. We try to make sure that the components don't care much about each other, but they care more about a coordinator. So this coordinator decides on how each component that are being integrated would behave. This conductor at this point is called the orchestrator. So this orchestrator controls the activity of each component. So this orchestrator serves as a central reference point for all their um, activities. So they remain unaware of each other. Orchestration helps with the integration of a set of loosely coupled reusable services to create a system that meets a new need. So, based on the control of the orchestrator understands the changes to each component that will provide a different kind of service. So, the orchestrator controls each component in order to ensure that there is some smooth operation, thereby ensuring that there is integration. Manage resources. So in this situation, we have something called a resource manager. The resource manager blocks every component from having direct access to some sort of resources. And that way, we have complete coordination of use of resource. So a resource manager is a form of an intermediary that governs access to computing resources. What could computing resource be? It could be a block of memory. So this guy is in charge of the memory and ensures that all requests or all attempts to use the memory must go through it, which is the resource manager. It is similar to the restrict communication paths tactics, because with this tactic, software components are not allowed to directly access some computing resource. But instead of directly accessing the computing resource, they place a request, they place a petition to this resource manager. This is the idea. They place a request to this resource manager. This is pretty similar to a few of the concepts you have in operating system, that we have component parts that try to make use of some resources. But even though we know that some resources may be available, some resources are strictly under operating system control. And as they are strictly under operating system control, it determines if they can gain access to such resources or not. All right, so here we are. We have our questionnaire as usual. So, what is the idea behind this questionnaire? Now that we are building components and we want to integrate them, it becomes important to check if it will be a smooth and a cheap integration. Remember, we talked about the time and the cost. So, this is really important. The goals for integratability are to reduce the costs and the risk of component integration. This is really important. The cost, the financial cost, the time cost, the effort cost, the risk of actually causing the system to fail. So these are the critical things that are controlled by integratability tactic. So here is our questionnaire. First is to limit dependencies. We check, okay, the system we are building, have we been able to limit dependencies? And then we check through our questionnaire checkboxes. Okay, let's just discuss a few of them. Does the system encapsulate functionality of each element by introducing explicit interface and requiring that all access to the element passes through these interfaces? So here is what it just means. You build a system, you have different components, you have different modules. The idea is this: all the modules, are they doing thorough encapsulation? Is there perfect encapsulation in every module? So in every class, is there perfect encapsulation? Are you sure that you're not leaking variables out that could be altered or modified from elsewhere? So this is just the idea. You check, okay, are we sure that we have a functional interface for communication? Okay, now this functional interface we have created, are we sure that it can provide the services it should provide? Or are there some component parts that can be altered without going through this interface? So if our answer is yes, then we say, okay, yes, we considered that, and it seems the tactic is implemented. Does the system broadly use intermediaries for breaking dependencies between components? For example, remove a data producer's knowledge of its consumers. So, because we have a data producer that tries to communicate with the consumer, what we say here is this: we don't want the producer to have direct access to the consumer, or else it will be bound to the consumer. There would be a reduction in separation. So what we try to do is we use an intermediary that receives from the producer and hands over to the consumer. So this is just a basic analogy that we need an intermediary in case we cannot completely eliminate dependency. Does the system abstract common services? So just like we said, there are times that we would have two components that have completely similar services, very similar services. So what do? We said we will do abstraction. Remove the component parts that are critical for their unique operation, such that the component parts that are not for unique operation are provided separately, and the abstracted part assists us in providing specific services. Does the system provide a means to restrict communication paths? So, are there ways to restrict communication paths to ensure that communication only goes through a specific path? Okay, so we don't need to sit here. Let's just continue. These are the questionnaires. You can easily understand this by reading them. So after limiting dependencies, we talked about adapting. So we can adapt our services We can tailor interfaces, and then we can configure behavior. Also, we can coordinate. Here we talked about the conductor. Remember, we said that we have an orchestrator that determines how components interact, how the components behave. And because of this orchestrator, we find a way to ensure that component parts do not think about other component parts, but they only consider the requirement of the orchestrator. So we check in our code. Do we have some sort of orchestrator? Tailoring. Tailoring interface for integrability. So we go to tailoring interface. By the way, if you remember, we discussed tailoring interface earlier. We just talked about it in a small sense. But we can talk about tailoring interface in more elevated way. So how could we tailor an interface for its functionalities? So the interface, as I said earlier, could be able to provide service to about 10 different components. The interface of a component probably could be able during integration to provide service to, let's say, a number of components. But the idea is that not all these components have the same level of service requirement. This is the key thing. Service component A can provide service for component B, C, D. But the problem is that component D takes a lot of input. Component D requires 40 objects with full details of parameters. But component B actually requires only one object and less than half of all the required parameters. So what can we do? We can make use of the tailoring interface tactic to make sure that that same component provides its service effectively to different components that require service from it, and at the same time it provides least knowledge of things that they do not need to know. All right. So an approach to that is by making use of wrappers. A wrapper hides the implementation details at the back of the scene and provides only what it is told to provide. That's a wrapper. That's a wrapper. So you have the system, you have a very nice box. It has many holes on it. And from this box, you can get 500 things at a time. But the problem is that we don't want to give everybody 500. So we make three types of wrappers. One wrapper has 2 holes, another wrapper has 30 holes, another wrapper has 500 holes. So if you want to give you only two, we carry the box, we put it inside the wrapper that has 2 holes. So at the end of the day, you get only two. And this is the idea behind the wrapper. It's an encapsulation whereby we redefine interfaces, asking it to provide just what the other component needs. A bridge transform assumption from a required state to a provide state. So we have two systems. One is making a demand, the other is providing some sort of service. So the provider provides to that who requires. Okay, but the critical part of the bridge is that it provides services that is independent of any particular component. For wrapper, it is not independent of particular component. It is depending on the component. So if we say component C and we say component B, but here is the main component. This is component A. It provides some service. So we have a wrapper that understands the requirement of component C, and so it determines how component A is presented to component C in functionality. Also, we have another wrapper here that understands how component B operates and the demands of component B, and so it always provides service to component B instead of component A directly. But on the other hand, we have component D. Component D makes use of a number of information such that it can get direct communication from component A. So in this situation, we call these wrappers. These wrappers are specifically for components. So the wrapper that is used on component C cannot be used on component B. If it is used on component B, it would provide much more information than component B requires, or it may even provide only some of the information that B requires while providing other things that B does not require. So this is the difference. In bridges are just defined generally, but wrappers are defined specifically. This bridge must be explicitly invoked. That means somebody, in the case of bridge, somebody must call the bridge. But in the case of wrapper, you don't need to call the wrapper because actually you don't know it's a wrapper. Actually, C thinks that this is A. B thinks that this is A. But D knows that this is A. So this is the idea behind this wrapper. Mediator. Mediator exhibits properties of both bridges and wrappers. The major distinction between bridge and mediator is that mediators incorporate a planning function that results in runtime determination of the translation. Whereas bridge establishes this translation at bridge construction time. So when the bridge is being invoked, a number of understanding of communication and translation of parameter values are done. But for mediators, the determination of what to provide is done at runtime, not at any bridge construction time or at any invocation time. Okay, let's stop here and have 10 minutes break. We resume after the break. Okay, I'm back. Let's continue from where we stopped. So, benefits of tailoring interface. All the three patterns we mentioned, the wrapper, bridge, and mediator, they help us in tailoring an interface to the demands of different components that try to interact or communicate with the component having this interface. So, they allow access to an element without forcing a change to the element or its interface. But they come with, as expected, some trade-offs. First is you have to do more work. Your code already is working, but just because you want to tailor an interface, you have to make modifications, and this is more developmental work. So you have to do more work, and then they would, by implementing this tailoring mechanism, you would somehow affect the performance of the entire system because the tailoring mechanism themselves make use of resources. The tailoring mechanism themselves, they use system memory, they use CPU cycle, and because of this there will be some overhead. Overhead means extra burden on the system. So two, we just mentioned two trade-offs, and then we've seen the advantage. The advantage or the benefit is that we get new functionality without destroying the current structure of the interface. So dynamic discovery pattern for integrability. So dynamic discovery applies the discovery tactic to enable the discovery of service providers at runtime. If you remember from the last class, we discussed this discovery tactic. We said the discovery tactic allows a user of service to be able to find a giver of service. This is the discovery tactic. So it applies the discovery tactic to enable the discovery of service providers at runtime. A dynamic discovery capability sets the expectation that the system will advertise the service available for integration and the information that will be available for each service. So here is just the meaning of this. For dynamic discovery, we have an assumption, and that assumption is this: if we have 10 services, 10 components that provide services, we have a belief that all 10 components would advertise their service. This is the strong points of dynamic discovery. If one of the components fail to advertise, then there's a problem, because dynamic discovery, which is something like automatic discovery, will not be able to identify that that component even exists. Or even if it identifies the availability of that component, it doesn't know what the component does. So cannot make requests of that component to get some sort of service response. So it allows for flexibility in binding services together as one. For example, services may be chosen at startup or at runtime based on their pricing. Pricing could be cost, maybe resource cost, or based on their availability. So with this dynamic discovery, it becomes easier to match service users with service providers. And since it is dynamic, right from runtime, we could have the system already working, because components can find each other as service users or service consumers also get access to the service providers. Dynamic discovery registration and deregistration must be automated, and tools for this purpose must be either acquired or must be generated or built. So with this, we are saying that since we want to use dynamic discovery, which means every component should be able to announce its service. As long as the components announce their service, then we will be able to find them dynamically. So it means that there must be some sort of registration. There must be a registrar that gets information of services and receives the service they provide in order to advertise it. This is important. Without this, the entire structure of dynamic discovery will not work. So dynamic discovery registration and deregistration. That means when a service is, when a component is available to provide a type of service, there must be an automatic registration that, okay, Mr. A is here and Mr. A provides this, and these services. When Mr. A no longer can provide the service, Mr. A must also inform this registrar that I no longer can provide the service, and with that, Mr. A is deregistered. That is this part. This is registered. This means add. You add it to the list of the available service providers that have been announced. And the registration means you remove it from the announced available list of service providers. All right. So, okay, we've talked about integration. Generally, we understand that systems are built up as component parts. These component parts, in fact, are built up of sub-component parts. These sub-component parts are probably modules that are built up of methods, classes, and what have you. And all of these try to work together. We have said that we need to integrate them in order to form a single system that works. But this integration is not as easy as it sounds, because we need to make sure that we provide the kind of service that is required by each component. And we say we do that by making sure that we have interfaces. We control this interface such that the interface must provide only the information required. And we said we can tailor the interface in order to do this. Also, we can ensure that this interface is the only part of communication such that we place restriction on it, that there is no other way of communication that must go on. And also, for us to be effective with this interface, we must make sure that there is no dependence. We always reduce dependence as much as possible. And wherever it is that we cannot reduce dependence, we must put an intermediary. This intermediary makes sure that only the least knowledge is still advertised. So, in example where a producer tries to communicate with a consumer, the intermediary stands in between in order to ensure that there is decoupling. The consumer and the producer codes do not get to tangle. All right. So this is the idea behind what we have done um, in this chapter. We can move ahead to something new. So, what chapter did we just finish? Okay, this is chapter 7, and with that, we proceed to chapter 8. Okay, so here we are, chapter 8, modifiability. Modifiability. From the beginning of our course, I think we already talked about some concepts that uh, are required to strengthen modifiability. If I remember well, we said one of them is modularity. We said it's important to make sure that we build our system in modular parts, because by building in modular parts, we will be able to make alteration sometimes later, and that alteration is what we call modifiability. All right. So we will discuss a number of things. What is modifiability? The general scenario. We will check for a concrete scenario, and then we will discuss tactics for it and the questionnaire for modifiability, as we have always done. Modifiability thinks about the cost and the risk of making modification. As simple as that. How much will it cost us to make modification? And what can we destroy when we make modification? The risk of making modifications. So, to plan for modifiability, an architect has 4 considerations. Number one is, okay, as we begin to develop our software, we believe that modifiability is an important thing. But what can be modified in this code later in life? Would somebody want to change the login page? Would it be the access to database that needs to be altered? Would we have to move the code that access the database to a different part of the main code, such that probably we want to enforce control? So a number of these things are the things that should come through the mind of the architect. Okay, if we say we have identified the parts that can change or parts of our software that can change in the future, the next question is, what is the probability of this change? What is the probability? Now, if you are developing software for a company that over the years, they have a reputation of thorough job. They present all the requirements, they present all the demands, they are well thought out. And when the system is built, usually the system is always already very good because there is thorough planning. And because of that, major changes are not usually expected probably in 5, 6 years. So the likelihood of change, if developed based on the requirements from such an organization, it's clear that the likelihood of change may be low. But on the other hand, let's assume that a software system is being developed for scientific purposes or for medical purpose. There's a very high likelihood of change. Why? Because these two fields are always evolving. These are two fields where research keeps going on and research keeps going on and changes keep getting made. And because of this, if software system is developed for an environment in which variable parts are still subject to modification and research, there's a very high likelihood that changes would be frequent. And so these are the things to think about. What parts can change such that we can decide on an appropriate structure for such a part. Now, if these are the parts that can change and some other parts are, let's say, written in stone and cannot change, then for those that can change, what is the probability that it will change and how frequently can it change? Okay, now when we have been faced with a change, who would implement the change? And what would be the cost of the change? This part of who will make the change is also quite interesting because we have some developed software systems that allow users to, using non-code tools, modify the software system just to the users. Example of it is a software system with a GUI that allows rearrangement. So you could go to edit mode and drag the UI components around. This is allowed. So by doing that, you are making sure that you are allowing a very high level of change, high level, high level change, which means it's not so detailed, does not require a lot of knowledge, does not require a lot of code. What just happens is that as the user moves about components on the screen, there's a callback happening behind. And this callback is changing coordinates of buttons, it's changing the dimensions of buttons, it's changing the location of code, and it's changing a lot of things automatically. We are familiar with this. I believe you are familiar with these systems that support callback, especially for those who program in C Sharp. C Sharp supports this callback of a thing. So with the callback, as you make modifications to GUI components at the back of this of the code, there is automatic code generation and automatic alteration of code. Then this determines what is the cost of the change. When you know what the change could be, let's take, for example, the last change that we discussed, the change that can be coordinated by the user. How expensive is this change? That is almost zero expense because it doesn't require any kind of complicated procedure. That is close to zero expense. All right, let's go forward. Change is so prevalent in the life of software systems that special names have been given to special flavors of modifiability. Some of them are scalability, variability, portability, and location independence. These are just different terms for modifiability. So, general scenario. As usual, we know that we have 6 components of the scenarios. The first is the source, the stimulus, the artifact, and after that, we have the environment, the response, and the response measure. Okay, let's pause at this time. Let's have about 5 minutes break and then we resume. I think I should have given you a break before starting this slide. Let's have about 5 minutes break and then we resume this slide. Well, no, modularity isn't essentially the ability to use a code for other purposes, but modularity supports that. In fact, modularity is very critical in order to ensure reuse. What you are talking about is called reuse, but modularity is the ability to have your system built into very small components that even if you want to reuse them, it does not require you spending 500 years to find which part of the code is also part of this function because you already built them at the beginning as a specific module. This module probably is a class. You call the class maybe save to database. So okay, if you have a keep of piece, you have group of code that you keep using, what you are doing is reuse. But if you keep using them every time, it would be better to actually make them as a class. That way, what you are doing is modularity because you just copy the entire class, you paste it, and you make some tailoring. You adjust it to the new use. Okay, let's have 5 minutes or so break. We'll okay. So this is 10:18. Let's say we'll be back by 10:25. We have a few more minutes, but it's better to relax and continue than to rush everything and then you cannot concentrate. Yes, it is good. It is good. The fact that you abstract and you make interfaces such that you can implement your abstraction or extend whatever it is that you have built is good. Yes. So I hope you are refreshed now. Let's continue. Modifiability general scenario. So for modifiability, we would have the source of the modification, and this is the agent that causes a change to be made. Most are human actors, but sometimes the system might be the one that learns or self-modifies. This is not so common till now, but obviously we will be going that in the next few years because of the prevalence of artificial intelligence. So what do we have? Possible values of source would be the end user, the developer, a system administrator, the system component itself, or the product line owner. So the start stimulus could be a directive to add or delete or alter a functionality. This is the stimulus. The source is the person who gave this directive, but the stimulus is the directive that was given. Artifact then is the code itself, the part, or let's say the class that was changed. The code, the data, the interface, the components, the resources, the test cases that needed to get altered. We have the environment as usual. It could be during code execution, that is runtime. It could be at compile time when we are building the executables. It could be at build time. It could be at initiation time. It could be at design time. Also, we have the response could be we made the modification, we test the modification, we deploy the modification. It could be a number of things, but here are just examples of possibilities. And then the response measure is okay, what now happened? It could be that amount of effort that was used, it could be the time spent on making the modification, it could be a number of things. Okay, so let's leave the abstract scenario and rush to a concrete scenario immediately. So we have a developer who wishes to change the user interface. Who is the source? It is the developer. Clearly, we can already see here that we have a source. This is our source. He wishes to change the user interface. What is he trying to change? He's changing the UI. And so what is this? This is the artifact. This change will be made to the code at design time. Design time. So what are we changing? We are changing the code at design time. So what is design time in this context? Design time is the environment. So this is the environment. It will take less than 3 hours to make the change. Less than 3 hours. So we are expecting that our response measure will be less than 3 hours. So this will be our response measure, and no side effects will occur. So we will make a change. That's our response. Okay, let's say we would make and test. No, not just make change. We will make and test the change. Okay. And so what else do we need? A software developer wishes to change the user interface. The change will be made. Okay, the stimulus is that the software developer wants a change. So it's just a wish. So we can say our oh, So we can just say the stimulus is a wish. So we can say this is the stimulus. So we already built our system. We have the source, which is the developer, who provided the stimulus, that is a wish to change. And then the stimulus is sent to the artifact, which is the user interface. This change will be made to the code at design time. So the environment that receives this modification is the design time. And the change would be made in less than 3 hours. This is the measure of such a response to the wish to change. And then we will make the change and we will test the change. And this is the response. Okay. All right, we have the developer as the source. You want to change. Okay, we accept it to be wish to change. It does not matter. Um, the artifact obviously is the UI because it wants to alter the user interface. And then the environment is the design time. We expect a response, which is that we do what the developer wants to do. And finally, there will be some response measure that it will be completed in less than 3 hours. Okay, tactic to control modifiability, goals of modifiability tactics. Probably we should start from there. The tactics to control modifiability have as their goal controlling the complexity of making changes, controlling the complexity of making changes, as well as the time and cost of change. So this is the goal of modifiability. Control the complexity of change, and then manage the time and the cost of the change. Yes, modifiability tactics has also three approaches. First is increase cohesion. You want to modify the code, make sure that each part of the code does just one job. Even if the part of the code will do one big job, and so it contains small tasks, make sure that these small tasks are also built into modules. Increase cohesion. Reduce coupling. Parts that should not be related are not related. Parts that can be separated are not forced together. This is reduced coupling. And then defer binding. Things that do not need to be joined as one now. Don't join them now. Wait till the last minute when they are needed. Okay, increase cohesion. The first approach to this is split module. If the module being modified includes responsibilities that are not cohesive, this is a very important thing. If the modules that you want to modify, or even before modification, if the modules of the system you are building now are not cohesive, example is you have a class. Let's say the class is print info. Inside of print info, you probably have a very small method that format text. So this formats the text for printing. And then the next line is display. This displays the text on the screen. That this makes sense, except that I have a strange line on the screen. So we have a display. Now in this system, if I proceed to have save to database, this is not right because this does not look like a component of my class print. And because of that, this is reducing the cohesion of the functionalities in my print class. So what do? I have to remove it and find an appropriate class for it to save it to database. So probably I have to create a class that does saving job. So refactoring the module into several more cohesive modules should reduce the average cost of future change. So actually, I think this is the better idea. We are not checking something that will be modified now. We are trying to prevent future difficulty in modification. So during the code development, we ensure that our modules are cohesive. They do exactly just that job. So what do we do? Next thing is redistribute responsibilities. If responsibility A prime and A prime are in different modules, then you should open these different modules, create a new module called A, and then bring all these duties back into A. This is the idea. If you have a specific task that is split over several modules, redistribute the responsibilities and bring them back to cohesion. This is the idea. They should be placed together. This refactoring may involve creating a new module that would now contain A and AA and everything. Okay, the next is reduce coupling. Um, we have seen a number of this in previous chapters. We have seen encapsulate. We have seen use intermediary in just the previous chapter. And also we've discussed services, that we must be able to abstract common services in systems that have similar services. We've talked about intermediary. We've talked about encapsulation. So next is reduce dependencies. This tactic restricts which modules a given module can interact with or depends upon. So in practice, this tactic is implemented by restricting a module's visibility and by employing authorization. So these are two tactics, these are two tricks for restricting dependencies. So if you do not want a module to have dependency on another module, first way to filter them is put authorization. All modules that do not have the authority to interact with the other module clearly are not given the chance. And from other modules, you can make this module invisible. You put it in a private environment. And also deferred binding. We can bind values at different times. Rather than binding values during code writing time, you can defer it till some later time, like at compilation time or at build time. Defer binding from design time. Do not bind at design time. So we can, at compile time or at build time, replace components, change the parameters of a component, and define the aspects of a component. Okay, the following tactics bind values at deployment, startup time, or initialization time. So I think we discussed this sometimes earlier, that configuration time binding assists us to make binding at the time the software system is being configured, most probably for the system on which it will operate. Okay, let's stop at the file binding. We have just about 11 minutes to the end of the class. So before I stop the class, I need to make an announcement one more time. Your assignment. I announced at the beginning of the class before a number of you joined. I announced that you could have one comprehensive assignment or you could have two assignments. If you want, well, based on my opinion, I can give you both assignments today. So you look at them and then you begin to try to solve them. Or I can give you everything as a single assignment, a very comprehensive assignment, and you submit on one day. But if I give them to you as two different assignments, given probably in the next few hours, you will submit one at an earlier deadline and submit the second one at a later deadline. So the general vote before a number of you joined the class was, okay, let's have the two assignments. So we submit whenever we finish. So not one assignment now, break it down into two, give to us the two assignments today, and then we will submit them before their individual deadline. I want to give the class a final chance to either approve that or to change it. If nobody speaks, then I agree that you want to continue with that. It To me it sounds sensible. So, any vote? And while you are at that, if there's no vote, you can write present in the chat and let's end the class. Two halves, all right. It seems two halves again. Okay, please write present in the chat so I can stop the class and we go. Now the time is 10:41. I'll wait till it's 10:42 to stop the class. No, it doesn't matter to me. It doesn't matter to me. I don't have an issue. You are not many in the class. If you are 100 in the class, it could be difficult to grade. But you're not many in the class. Actually, I prefer to give students two because you don't have some sort of accumulation of tasks on you. You solve the first part, you submit it, you have some sort of relief. Normally, I prefer to give it to you as two. I personally would prefer that. Okay, if these are all the students that are present, I understand the fact that others are physically in the meeting but mentally elsewhere. So I'll be stopping the meeting now. See you when next we see next week.